Okay, then we learned, we learned there's three conditions when limits don't exist. Again, the one we just talked about. When the left-sided limit and the right-sided limit don't agree, then there's no limit. Again, the perfect example is like f of x. F of x is the square root of x over x, and we're taking the limit as x approaches 0. Right? That's the case where it's going to look like it's approaching 1 from the right and negative 1 from the left, so there's no limit. The second situation is when it looks like the function is veering off towards infinity or negative infinity. You know, usually like when you have a vertical asymptote, that's what a graph does. Something like that, right? If I take the limit as x approaches 0 here, it's going off towards infinity, which is kind of, by definition, not limited, right? Infinity is not limited. It's unlimited. And then the last one is oscillations. And it's not just any oscillation, because we've seen things that oscillated before. When we were in chapter 4 doing word problems with trigonometry, we did harmonic motion. Harmonic motion is where you'd take a ball on a spring and then let it drop, pull it down and then let it go up and down and up and down. Okay? That's harmonic motion. That's not necessarily the kind of thing that doesn't have a limit. The example they gave was actually this. F of x is the sine of 1 over x. And then they were taking the limit as x approaches 0. I mean, because the x is in the denominator, you can never let x equal 0. But as x gets closer and closer to 0, this thing is getting really, really big. So if the closer it gets to 0, the shorter the wavelength gets. So over here, or the period, over here maybe it was like that, and then it got closer and closer and closer, and then, just gets back and forth and back and forth. It's infinitely close together as it gets closer to 0. That's the kind of oscillation that doesn't have a limit. That's why I'm just calling it wild oscillation, not just any old oscillation.